Let's look at a logarithmic quadratic equation, if that's such a thing. Okay, solving an equation where the variable is in the exponential level. Remember that we always have two approaches to this. First of all, look at the bases. Okay, we've got two bases here that are not the same, but they are powers of the same, that can be written as powers of the same base, right? So I can rewrite this, even though, 9 is a power of 3, 81 is a power of 3, but 81 is also a power of 9, right? So I can leave this term the way that it is, and then over here I can write this as 9 squared to the x power. And powers of powers get multiplied, right? So now I have an expression where I've got two bases that are the same raised to two different exponents, and the only situation in which that is possible is if the exponents are equal, right? So we're basically dropping the bases completely and just solving for x now. Now that it's a quadratic equation, we're just solving this like it's a quadratic equation. It's not an exponential equation anymore. So let's move 2x over to the other side because we solve quadratics by setting them equal to 0, right? And then we start trying to find the zeros of this equation, right? So what can you do? You can graph it and find the x-intercepts, okay? We can use the quadratic formula because it's quadratic. We can factor, right, using the zero product property. Is it possible to come up with two numbers that multiply to be negative 15 and add to be negative 2? Yes, it is. Negative 5 and positive 3. And the 0 that comes from here, based on our work in a previous unit, we know that the solution here is 5, and the solution here is negative 3. Okay, so we get two solutions to that. All right. The alternative method for this, right, as we go through here is once you identify that this equation has variables in the exponential level, the only, well, I shouldn't say the only way. One way to solve is to get that exponent out of the exponential level, okay? And you can take a logarithm of both sides to make that happen, right? Because remember, logarithms are exponents. More specifically, they're the inverse operation of variable exponents. So I can take the log of both sides, and the logarithm that I take is totally up to me, right? Now, in this case, because I recognize both of these are are powers of the same base, like for example, 9 and 81 are both powers of 3. So I'm going to, for the sake of example, I'm going to use log base 3 here, okay? Now, when I take a logarithmic operation to both sides, the exponents come down in front, and we'll leave those in parentheses here, okay? So now we have log base 3 of 9 equals, this x comes down in front. I can put parentheses around that too. Log base 3 of 81, okay? And we can evaluate each one of these logs. So we end up with the log base 3 of 9 is 2, because 3 squared is 9. And over here, log base 3 of 81 is 4. So now I have, again, a quadratic equation that ends up being 2x squared minus 30 equals 4x. I can subtract the 4x over to the other side. Okay, and again, I kind of took a roundabout way to do this problem, but just for the fun of it anyway, right? All of these are even numbers. So because they're all even, I can divide everything by 2, and 0 divided by 2 is still 0. So we end up with the same equation that we got here. How's that for spacing and timing, right? So we can either write the powers as powers with the same base, or we can take a logarithm of both sides, okay? The logarithm that you want to use is your choice. I could have used log base 9. If I had done log base 9, this would have been a 1, right? This would have been a 2, and I would have ended up in this space a lot sooner, okay? I could have done natural log. That would have been a little messy, but it could have been done, right? So be careful with the logs, with the bases that you choose when you're going about solving in that fashion.